I have 20 minutes or
Yeah, yeah.
20 minutes. Okay.
20
Is there
minutes.
a way you can share the my slides and I can
Okay. Presentation है उनका. Please share the presentation if you have. Yeah. Yeah, the slides visible to you?
yeah, but do you have my presentation?
Yeah, yeah. It's being projected here.
Oh, perfect. Okay.
Yeah.
Could you go full screen? Okay, that is perfect. Thank you so much. So I have 20 minutes and I'm going
You
to make
can prompt for the next slide, please.
Perfect. Thank you so much. So welcome everybody, and thank you for the opportunity to attend this conference. So the presentation that I'm going to hold is going to be about innovating the PEM electrolyzer stack and efficiency and longevity. My name is Huron, and I am the founder of Casco.co.uk, and I'm also the founder at Hydrogen Training Solutions. And I nicely balance my time between these two companies, 50-50. And I will give you a little bit of story of the Casco.co.uk, but Hydrogen Training Solutions is an organization which I started about a couple of years ago, and I run training courses and workshops about PEM electrolyzers, about the balance of plant, about the stack, and I've run that to help people innovate and to allow companies to train their staff a lot more efficiently as engineers who already have skills in PEM electrolyzers is relatively few and far between. Can I have the next slide, please? Next slide, please. Thank you. So I'm going to make a very bold statement here. So most expensive part of the PEM electrolyzer system, as the complete system is concerned, is the PEM electrolyzer stack. And it typically currently only lasts for a very short period of time, typically a handful of months. And this is really bad, because what we're promised is 80,000 hours, which is around 10 years of operating time. So that's similar to buying a car, when you would expect the car to last for about 10 years before you start to have issues with the car. And in fact, it actually breaks in about 6 months. So the engine just explodes in 6 months. That would be a terrible deal. And I think most people would think that this is something that would make you unhappy about the product, and it wouldn't justify buying it. Could I have the next slide, please? So just so this is not coming from me only, I'm going to give you somebody else's opinion. So this is somebody else saying that the durability of electrolyzers is one of the main challenges in their widespread commercialization, although many commercial PEM electrolyzer manufacturers would claim durability up to 30,000 hours or even longer. So these people are saying that even 30,000 hours claimed by the OEMs or the equipment manufacturers is long. However, so I'm just showing you this so that it's not just coming from me. I'm backing it up from this particular source. Can I have the next slide, please? So this is what it looks like. We've got 80,000 hours on the left, which is what we're being promised, but the actual performance is very, very low. So what this does is it throws in a massive issue, a massive bottleneck with our LCOH, so the levelized cost of hydrogen, because for the levelized cost of hydrogen, we factor in the capex and we factor in the opex, but most projects are not aware of the fact that in reality we have a lot of other things going on, such as the lack of innovation, or the innovation that is needed, desperately needed, as far as stacks are concerned. Could we have the next slide, please? So why this this prevent the widespread of these projects all over the world? Well, what we have is we currently are recovering from a number of OEMs reporting very similar things. If you look at some of the OEMs' earnings reports, and they're looking, what they have a lot of times is you see manufacturing catastrophes. So where you see products that are being made which are simply not fit for purpose oftentimes, and they are manufacturing these very, very expensive stacks, and they're not fit for purpose, and they need to be they need to be disposed of a lot of times because they are not fit for purpose. And what we've seen for there's one particular OEM which has reported that they produced a specific stack iteration which had over 50% failure rate before it was even shipped. And the second would be the data blind spots. So when we have very, very limited real world data, up to around 40 or 80,000 hours. So we don't know how these electrolyzers, how these large scale PEM electrolyzers are operating at the 5 or 10 year mark. And the only real-time data that we know with large-scale PEM electrolyzers, I'm talking not lab-based PEM electrolyzers, because in lab-based, I understand that in a lab we know how it operates up to about 10 years for quite a long time. But that is in a lab, small scale, low current density, high catalyst loading, thick membranes, a very, very lenient operation. But we don't exactly know how it operates in a large scale, high current density, high pressure conditions in real time over 2,000 hours. So currently, over 2,000 hours, there's very, very limited public data out there about how these electrolyzers operate. So the inefficiency and longevity is also affected because, like I said, in the lab we know, but these do not. So in the lab, the operating conditions in the lab do not reflect the demanding and the cost-effective operations, i.e., high current density, high efficiency that we require out in the field. Could I have the next slide, please? So why does this prevent the widespread projects from being implemented? Well, the financial reality kicks in because when you buy an electrolyzer and you have a very large cost of replacing the stack, which is initially unanticipated, then the reality is going to hit, and it's going to make the ventures financially unviable. So if you buy an electrolyzer, a lot of times your business model does not take this into account, and it's going to not be sustainable. Could I have the next slide, please? So how does a PEM electrolyzer actually work? And I have a very, very limited amount of time, but I would like to show you how this works. So initially, we've got the water going into the electrolyzer cell on the anode side, and PEM stands for proton exchange membrane. It also stands for polymer electrolyte membrane, but we're going to stick with the definition proton exchange membrane. So there's a membrane, and this membrane is a polymer membrane. It's a perfluorosulfonic acid polymer membrane, which is going to have a very interesting property. And the property is that it conducts protons. It allows protons to be exchanged through this membrane. So once we reach the minimum voltage, there's going to be something very interesting that will start to happen, and the protons will start to go from one side to the other side of the membrane. So first we're going to have water splitting, then we're going to have the ion exchange, which is the protons going through the membrane, and on the other side, these protons are going to mix with an electron, and they will and hydrogen gas will be forming or evolving, as they say. Can we go to the next slide, please? So what we see here is this is just a very typical balanced plant of a PEM electrolyzer, and you can see the PEM electrolyzer stack somewhere around the middle of this diagram, and you can see the water being pumped through the PEM electrolyzer stack, and that is the main component of the electrolyzer. All the other components are just there to support the PEM electrolyzer stack. Could we have the next slide, please? So over here, you can see the proton exchange membrane, and you can see the cell surrounding the membrane. And you can see the arrow showing that on the left, you can see the arrow showing the H2O, so the water going through the anode chamber. And as the water is going through the anode chamber and you apply the voltage, which once you reach the threshold voltage being the minimum voltage where thermoneutral electrolysis is going to happen, and that voltage is going to be 1.48 volts in a thermoneutral situation. In a very large scale situation, it's probably going to be slightly higher because it's not ideal conditions as such. But you're going to have the minimum voltage or the threshold voltage where this hydrogen atom is going to be split. So the electron is going to be split off from the proton. And now the proton is going to be so tiny that it's going to be able to go through the proton exchange membrane because the electron is removed. And the proton is positively charged, and also the anode chamber is positively charged. So the anode chamber is going to repel the positively charged proton into the cathode chamber, and it will cross the proton exchange membrane. And the cathode is negatively charged, so the cathode, which is negatively charged, is going to attract the positively charged proton into the cathode chamber. And the electron is going to actually go through the electrical connections. On the right-hand side over here, you can see the PSU, and which is the power supply unit. So the power supply unit is going to have the electron being transported over to the cathode chamber, because what is electricity? What is current? What is current? Current is the flow of electrons, right? So the electron is going to go through to the other side with the electrical connections. The proton goes through the proton exchange membrane. Proton and electron meet on the other side of the membrane, and boom, we have hydrogen. So that's a hydrogen atom, and it will immediately form into an H2 molecule. So over here, I also want to point out that we have the anode chamber, which is the anode chamber is going to be not pressurized, because we're just going to have the water and the oxygen staying on the anode side, and the hydrogen side, the cathode side, is going to be pressurized. So what we're going to have is there'll be a little bit of hydrogen going back into the anode chamber. And this little bit of hydrogen going back into the anode chamber is relatively safe, and we can keep an account of that. And at the start of life, but at the end of life, as we have a lot of membrane degradation, we are going to have what's called membrane thinning, and we'll go into that in just a second. And this membrane thinning is going to cause us to have increased hydrogen going back into the anode chamber, and we don't want hydrogen going back to the anode chamber because there is oxygen there, and that can cause an explosion. That's going to cause an unsafe situation. Could I please have the next slide? And could we watch this video, please? If you just press the forward arrow again, please. So what you see here is the amber part is the membrane. You've got the anode on the left, you've got the cathode on the right, and on the left you've got the anode chamber. You've got the H2O coming in, the hydrogen splitting off, and you can see the electron wheezing off to the top, and you can see the red proton going to the other side of the membrane and joining the electron on the other side of the membrane. Thank you. Could I have the next slide, please? Perfect. So what we see here is for innovation. This is where the innovation is needed desperately. Currently, we've got quite a lot of issues with the membrane thinning, because the membrane in the PEM electrolyzer is already very, very thin. And if we have any degradation on the membrane, that is going to cause even more hydrogen going back from the cathode chamber into the anode chamber. And if this happens, so if we have too much hydrogen going back from the cathode chamber to the anode chamber because of membrane thinning, then we are going to hit a situation where the amount of hydrogen is going to be too much in the anode chamber. So we can handle up to 2% hydrogen in the anode chamber according to the ISO standard on electrolyzers. Up to 2% hydrogen can be in the anode chamber, but if we go over 2%, that is an unsafe situation. We must shut down. So if the stack reaches the condition where the membrane thinning has reached such a state that the hydrogen transport back into the wrong way is too much, and we have to shut down, and that stack has come to the end of its life. Okay. And how does that happen? Well, we have first hotspot formation. So hotspot formation is going to be caused by literal hotspots on the surface of the membrane, because the surface of the membrane on the anode side is going to heat up drastically. That's where we lose most of our energy. That's where most of the inefficiencies are, the surface of the anode chamber. And that is we can overcome that by using better catalysts. We can also overcome it by having much better water flow. How can we achieve much better water flow? By creating stacks which are which we can hydrate much more easily. A lot of times the way we can achieve that is by using stacks which are smaller, which do not have so many cells in them. Okay, so we also have the water conductivity. So we need to have really good water quality in order to prolong the stack lifetime. Could I please have the next slide? So our journey in our company, casco.co.uk, is that we've identified how critical and devastating the impact of stack failures and the issues with the hotspot formation and the issues with the low water conductivity.
5 more minutes, please.
5 more minutes. Thank you. Thank you. The devastating impact of these degradation mechanisms to projects is great, and therefore we've understood quite a lot of these failure points, and this led to the insight of using redundancy systems. So what these redundancy systems are going to do is that we're going to use smaller stacks. And can I at this point just have the next slide, please? Sorry, can we go to the next one? And we'll come back to this in a second. So this is our stack, and this is a 20 kilowatt stack, and essentially for a 1 megawatt system we would use 50 of these stacks. Now, because we are using smaller stacks, what we're doing is instead of having 100 cells in a stack, we've got 10 cells in a stack. Why is this an advantage? Well, I'll tell you why it's an advantage. Because it's an advantage because in each stack it's much easier to achieve a really high water flow rate. The water flow rate is extremely critical to reducing hotspot formation and to enhance longevity of the PEM electrolyzer. If we have a smaller cell count in the stack, then the same flow channels are going to have to only hydrate 10 cells rather than hydrate 100 cells, which means that we can achieve 4 times higher water flow rate across each stack. and that is going to reduce our likelihood of hotspot formation. And this is going to cause the stack to have a much longer lifetime. In addition to that, because we are using less cells, we are statistically going to have a 10 times lower failure rates. And in addition to that, we also have the ability to run in redundancy. So if we have any issue with one particular stack, we can isolate that stack and we can keep running the rest of the system with no problem whatsoever. This is already done in solar. This is the whole basis of solar. And it's already done with AEM electrolyzers. But for some reason, we haven't noticed that this could be done in PEM electrolyzers. Can we go back to the previous slide, please? Thank you. Sorry, can we go back to the previous one? So two before this one. Oh, we're going the wrong way. Yeah. Thank you. That's it. This idea of the redundancy of what I've just explained, we have built our business at caxo.co.uk. So we've got our main investor, who's Peter Gregory, who's also our co-founder and commercial director. We've got our head of engineering with a mugshot there, and we've got our head of process, and this is our leadership team, and we've got a lot of we've got a lot of contractors also that we use alongside. Okay, can we continue to two slides on, please? Thank you. So our approach is we want to have much less cells. So we want to have 1/10 of the cells. So instead of having 100 cells, we want to have 10 cells, and that's going to allow us to have 4 times the water flow, reducing hotspot formation. Also, lower statistical failure. We are going to have the manufacturing repeatability, and it's going to also give us the mass production readiness for our technology. Can we please go to the next one? So in order to for us to drive the innovation beyond the 60 and up to the 80,000 hours, we need a lot of innovation. And I think I'm going to run out of time here, so I'm going to probably stop at this particular slide. But I'd like to just say that if you look at Tesla, for example, what Tesla does is about 20 years ago, when Tesla was just a startup company started up by Elon Musk, people were saying, there's GM, there's Ford, there's Toyota, there's very large car manufacturers. Why do we need a small Silicon Valley startup? That's what everybody said at the time. And what Elon Musk said was that, where is their electric car? Where was their electric car 20 years ago? There wasn't one. Innovation happens at small companies. Very, very large, out-of-the-box thinking happens at small companies where innovators sit down and they put ideas together which actually work. And I hope that with this conference, all of you are going to improve a lot your innovation talent and your genius. And if you are very interested in PEM electrolyzers, I would love to hear from. I would love to. I'd love to hear from you. We can have a chat. Let me know. Just wishing you the best in your future of innovation and engineering. Thank you very much, everybody. I hope you enjoyed this presentation. Maybe I'm not sure if you'll get the slides afterwards. I hope you do. If not, you can also let me know at the end of this slide. My contact details are on there. It's hk@hydrogentrainingssolutions.co.uk. Also on our website, which is something I didn't get to cover, is there are a couple of free apps that you could use for stack simulations to help you understand how stacks works. And these are on hydrogen20solutions.co.uk. My contact details, my contact email is hk@hydrogen20solutions.co.uk. Can we just go back one for a second, just on the previous slide? Thank you. So we have a free masterclass. If you are interested about PEM electrolyzers, have a look at our free masterclass. It's a 2-hour free masterclass going to take place on the 29th of September 2025 at 12 noon UK time. It's free to attend. Also, you can register at hydrogen20solutions.co.uk.
Thank you, Mr. Yunus, for an enlightenment talk. And you also touched upon the power of innovation. Innovation always creates newer avenues for research, and the audience must have really taken a cue from your expertise and innovative approach towards hydrogen technology. And hopefully, one of the students who are here will register to your online and in-person lectures. Thanks so much.
Yeah, thank you so much for having me.
Moving on, the next lecture for today is from Mr. Lakhan Lal. He's a research scholar from Israel. Topic being from electronic structure to conductivity, computational studies of OER catalyst for green hydrogen production. For the benefit of the audience, I would like to introduce our speaker. Mr. Lakhan Lal is a PhD student at Technion, Israel Institute of Technology, Haifa. He specializes in computational material science, focusing on functional metal oxides and metal organic frameworks for applications in electrocatalysis and photocatalysis. Under the guidance of Professor Michael Caspre, he is developing a non-equilibrium Green's function formalization to model energy conversion materials. Previously, he contributed to the development of ceramic composites for electrolysis applications at the National Institute of Technology, Karnataka, India. His research aims to enhance the efficiency and sustainability of green conversion device. Over to you, Mr. Lakhan Lal.
Thank you. Thank you very much for the nice introduction. So I will share the screen. Just a second. Okay.
Would you be presenting from your end, or should we project your slides?
I'm presenting from my end. Yeah.
Okay, thank you.
So just a second. Okay.